We start with our very important speakers, Dr. Georgios Katalagarianakis. We're really pleased and honored to have him at the school. Georgios worked at the European Commission, and he is responsible really for making sure that the nanosafety research field and community really evolved. Georgios raised hundreds of millions of euro for nanosafety research. So without him, we would not be here today, all these 20 projects. Georgios is a philosopher by heart, so his presentation is a philosophical reflection on SSbD, where it came from, where it goes. Georgios, the floor is yours.
Thank you, Danail. Yeah, I was put at the end of the school. As the old saying say, the opera is not over until the fat lady sings. So I'm not so fat, but anyhow, not even a lady. But the saying passes here. Well, welcome to this morning session, the hard nucleus of this society. I'm very pleased to see you, especially very pleased to see so young faces attending the school. We definitely need this new blood, if I may say so, because I have seen very successfully the past week a passage from what used to be exclusively nano to what now is defined as advanced materials, and most important of all, chemicals. So this is our scope, and my intention is to find some brains among yourself, push the start button, because whatever I'm going to say is based on the past. But we are not talking about the past, we're talking about the future. And what counts for the future is this new critical capacity. So that's my objective. And we don't need to have all critical capacity, some critical capacity. Okay, let's go fast. As you have understood very quickly, we are talking about rules, be it hard law, be it soft law. These are rules. How do we do the test? How we will do that? It's standardized, benchmark, interlaboratory, everything, but it's rules. And rules have been around since very, very early times. I mean, every book on safety will start from the Code of Hammurabi, may have heard of, Middle East, Mesopotamia. I think we have very simplistic rules. If the house falls and the owner is killed, then the entrepreneur who built the house is also executed. Performance-based, no technical requirements, nothing at all. Very simple. Of course, we are much, much more progressed than that, and we are still on rules. So, first conclusion, after a couple of minutes of talk, if you are in an area where rules do not exist or are not respected, come on, work first on this item. And the guiding principle for the rules is that the rules are always applied, created and applied, hopefully, when one group conceives another group as not responding to their expectations. Simple. There is no legal issue there. There's nothing at all. It's very simple. You have one group whose confidence is not enough against the other group, a rule comes in the middle. The rules are space-dependent and time-dependent, so they change with space and time. They're based in the past, like my talk, and concern the future, so they have to be continuously revised. Next, question comes, okay, we all agree safety is needed, but how much? So the question is not really how much safety, because the moment you say, I want that much safety, there's always somebody who will say, well, we can make better than that, and we should make better than that, and this and that, and moralities, and so on and so on. So where do we stop? We have to stop somewhere. So a good criterion is the answer to the question, what resources am I prepared to pay today for not my pleasure of today, but my pleasure of tomorrow? And this is very, very significant, because the resources that you have today can be put on something that you are needing already. If you are in government, you may wish to put resources for a school or a hospital. So why to improve the safety of a road more than a certain limit when the same resources can be put in the hospital? So there's always a balance. And coming back to the question, how safe is safe enough? The question is not relevant. The question is, how much resources of today am I willing to put for my safety, my benefit of tomorrow? And in order to do that, you need a guide. So the guide that you may take is the societal value, rather the value that the society attributes to human existence and human well-being. Is it stable? No, it depends. One society may have this standard, another society may have a different one, a different value. In other words, if you're worried about your existence today, you don't really worry about something that may happen or may not happen in 10 years' time. And here we have my second conclusion. Safety is a moving target. By the way you launch a project and you reach the results, your goal has moved. You're no longer there. So conclusion number 2, pardon, be ambitious. Especially in safety. Don't try to solve problems of yesterday. By the time you finish, you will be outdated. Go ahead. 10 years ahead, maybe it's too much. 7 to 8 years ahead is a good horizon. Let's go forward after this second conclusion. And by the way, if your safety or your society is high enough, then society is much more concerned about new technology, because they don't know what this may bring to them. And their value of life is already high enough. So they will be always unwilling to take new technologies on board unprepared, which means that you need to have the answers before the questions. It's like Woody Allen in a film. Woody Allen was going around with a drink in his hand, and suddenly talks to the camera and says, I've got an excellent answer, but nobody asks me a question. It's something like that. So you have to be prepared for your safety answers before you launch the technology. Let's move on. So what happens with the materials and the safety of them? So far, especially for the chemicals, the model was a kind of linear model. You have a chemical, you study it, you make a risk assessment, you send the file to a service, the service looks at it, approves it, and then you are able to commercialize the material, as simple as that. Okay, good. Question is that we have something like 200,000 chemicals. And until we finish all this linear model, let alone that we need a lot of people in the business side and a lot of people on the service side, and the service side has to take the data of the business side, and they are never sure, so they may ask this and ask this and ask that. So it will be year 2200 before we finish with the existing chemicals. So good model does not work. And we have 4,000 to 5,000 chemicals new per year. And we test them one by one, but they don't act one by one. We have additive effects, so several chemicals which end up to the same toxicity endpoints, like endocrine disruptors, for example, or nitrates. We have the allergies, so they are dangerous to a group of people, but we don't know the mechanisms. And we have the additive, so exposure over several years. And these are, let alone the triggering, so you have a relatively safe, but this safe material, but this in connection with something else, like plastics, they give something different. So my number 3 conclusion, simple systems are nice, but they have limits. So we have to go beyond those. And I'm afraid that here I reach my last conclusion, because from now on, we are in a bit unknown territory. What is this territory? So we go then to complex systems. Remember that the previous 3 conclusions must have been solved already before we go into attacking the complexity of the system. So nano is a good example. We have about, 10 sectors, about 8 legal frameworks, like, respirar atmosphere, food packaging, medicine, you name it. And one item in one will necessarily affect another unexpectedly. And this is typical characteristic of a complex system. The first thing, of course, that comes to mind is, can we engineer the risk out? Like, for example, we have seen these windmills, which have a gear system of about, 10, 15 tons. They are on top, and lubricants and so on. But now we have permanent magnets, which do not need heavy gear systems, and surely not lubricants. So first approach, but you cannot engineer everything out. There's always something that continues to be there and has to be governed. So we are now entering the governance, not governance as act of government, but governance as scientific field of managing a complex system. Small parenthesis, Alan is not there to listen pleasantly to my Aristotelian analysis, but I'll do that. The first who talked about governance is Aristotle, year 380 BC, and he took as example ship governance. So the skipper, the governor of a ship. The story, of course, why? You may ask why? Why a ship? The story is about 100 years earlier, when the navy of Athens was created by Themistocles, but this is a different story, it will consume some time. So let's come to Aristotle. Aristotle then defines the responsibility of a governor. By the way, governance is kybernetes in modern Greek pronunciation. In ancient, that would be kubernetes, if I'm not mistaken, which was taken by the Latins, became gubernator, governator, governance, and government, and all these things comes from the ancient, until a new complex system came forward, and that was the computer and the operating system. So they were looking for a word to express this complex system, and they found it, and now we have cybernetics, which is essentially the same thing, in word and in methodological approach. So what is then a complex system? Aristotle says, well, we have things that do not change. First, our destination, our goal. Second, those that we cannot change, the distance to or the goal. Those that change, but we cannot do anything about that. The waves, the wind, the sea situation. Those that we can change, but before we leave, our provisions, our crew, our supplies, and those that we can change on the way to our destination. So, coming back after this parenthesis, how we can classify it in nowadays governance of complex systems. The first thing we have to do is information, indeed. Let us know what we are doing and let everybody else know what we are doing, and let's inform what we are going to do next. That's the information. So in our terms, that will be database, test results, practices, standards, all this information, roadmaps, and so on. Communication. That's the second target in governance. We have to tell and be informed what we have in common and work on those so that a field or a part of the road that we can go together, we can join forces. Number 3 is planning. Remember, I say number 3 because I put the goal apart. So where do we go? What is our target? And in safety, we may, or our targets, and in safety we may have some conflicting targets. For example, you design a system for fire, but you make it very vulnerable to explosion, or vice versa. So smoothing out the targets, our destinations, is a prime goal, and we shall see in sustainability that this is far more serious. Number 3 element, therefore, information, communication. Number 3 is planning. What is our strategy? And planning goes together with the resources. So what resources we have, what can we realistically achieve? Critical element in the planning is our past experience. So have we done this in the past? And what has this given us? Talking about chemicals, information about complex systems is scarce, peculiar. You can find a lot of characteristics, but we have other sectors who have gone through this, sometimes without really knowing it. But having a look on what other sectors have achieved is a good drawing of knowledge and experience, and of course translating it into our theme. Number 4 and last operation is our control to the destination. Do we mark progress? And as I said before, the destination in our field is moving. Where is it expected to be in 10 years' time? And depending on the material you are studying, you may be surprised. Ask yourself, who was talking about microplastics 10 years ago? PFAS DDT, asbestos, no safety is finished without the word of asbestos. There was a book in 88. It's available in Google Books free of charge. About asbestos, it was concluded that this is the most solid business ever. They have nothing to fear. There is no alternative to asbestos. Perfect sector. 6 years later, asbestos was banned. So be very, very deep looking and look into the societal requirements. And by the way, about 15 asbestos are around, different materials, all of them, and 2 or 3 are carcinogenic, but all of them are banned now. Complex system. What do you expect? Governance, therefore, I will not take long because I have to move on to sustainability. And sustainability, there has been quite a long time talk about that. I can remember the European Union Council of Ministers 1992. They defined competitive and sustainable growth. It was a kind of contradiction in terms, but anyway, let's not discuss this now. And then there was a big fuss, this and that, and 10 years later, and sometimes total distortion of objectives. So 10 years later, 2002, was a building conference, United Nations in Oslo, and there was a conclusion that all our buildings should be made in wood because marble and granite and cement are non-renewables. This marble. I was trying to explain that we have marble on Earth until the humans disappear in the next life extinction. I don't know how many millions of years, I hope many. No way. No, marble is non-renewable. Okay. So, pointless to ask, to discuss with those that take it dogmatically. Helpless. Anyway, in sustainability, therefore, we have the basic problem of hierarchy of goals. People understand it differently, and on top of that, those goals move on. So how do we define where do we want to go? We have seen some nice examples about absolute sustainability, very elementary, I may say, but it's a first approach to define what we are talking about. And surely it's not the end of the story. So conflicting goals is a major item in sustainability. The next item is global. It's a global target because it does not make any sense to have a perfect garden in your house, which is totally sustainable, but your neighbor is totally unsustainable, and there is an open market between you two. So before you realize it, you will be kicked out of the market, one way or another. So it's a global issue. It's one planet. So we have to, by the way, the planet absolutely has no problem with the things we do, very easily can kick us out. But we have a problem on that planet. So the problem is ours. I don't like mixing the planet. The planet will survive, has survived even worse things. Then defining your system. That's the most critical part. That I consider is extremely, because it's very difficult to define system boundaries. Everything is related. I said it's already unknown ground, so I will not make more than how to say that, a gross approach to the problem. But let's take one item of sustainability, the material supply. It was lately that I saw the prices of antimony You know the prices of antimony? $40,000 a ton. I was mining engineer in the beginning of the 80s, and antimony in our metal was zinc oxide, and lead oxide, and silver, and gold, polymetallic. It was penalized. You had to pay somebody to take it. So if somebody smart enough would be paid at the time, I don't remember the formula, but it was quite significant. So something, say, a concentrate of above 1.5% antimony was not soldable. You could not sell it. And antimony now is a critical raw material. In general, we have a big problem in materials move on this planet. And the reason is that materials have become very, very cheap. Very, very cheap. I mean, which material can I have? Copper. Copper used to be in antiquity around 7 drachma, which is 7 drachma. 1 drachma is a labor day. So something like 700 euro a day, a kilo. If we assume that a labor day is 100 euro, but not gondolieri of Venice, because gondolieri is 90 euro a half hour. So that's entirely different scale. Right, so critical raw materials, you can name a lot. Antimony is now used in batteries and so on, also in the military. Lithium, lithium at the time that the batteries came forward was something like 8 million ton no deposits. Now they are about 80. So people start looking for them. But one wonders, why on earth did we take lithium batteries? We could take potassium batteries. Potassium is only 5% less in reduction potential. So, I mean, okay, it's a little bit bigger item, so it could be something like 10 or 15% larger in volume for the equal energy capacity. But why on earth did we not take potassium? Or sodium, another 5% down, but I mean it's far more on Earth, everywhere. Or rare earths, you know about rare earths? Rare earths, like the Holy Roman Empire, which was not holy, not Roman, not empire. They are not rare and they are not earths. Why are they called rare earths? Because the original name was rarely mined earth minerals, which means that nobody was looking for them. All the geological maps, why to map a mineral that nobody is using? Of course not. And then suddenly we need niobium, and we need lanthanum, and we need this and that for the permanent magnets. How's that called in memory? So material supply is something that ought to be taken on board right on the design stage. When you say, I'm going to make, I don't know, aluminum cars. Okay, first question, do we have aluminum? Or lithium batteries, do we have lithium? Right, and then what do we do next? Well, either you don't make batteries on lithium, or at the same time that you start the research on batteries on lithium, at the same time you launch a geological research to find lithium deposits. Otherwise, you are there with a problem. So attacking a problem on its beginning in the design phase is a must and very rarely done. Okay, my last item, in a few minutes, I think I have. 3 minutes? Excellent, 3 minutes. What do we mean by design? By design. What we have seen very often, and I believe there was no other option, is an iterative risk assessment, an iterative study, an iterative. So what I was saying earlier, that in the very early stages of research, we take the complete system, we define its boundaries, and we study that system entirely. But that's not safe by design or sustainable design. Anyway, safety is a part of sustainability, but let's not open this discussion. The first thing that you need to, but we have to move on from this stage gate model, which is fine, already begins to show its age, but it's a normal thing. The advantage is, of course, that several people get accustomed with that. So immediately you gain audience, but we have to move on. So what by design means? First, like in governance, we need to know our target. What is the target? How much do we spend to make this building safe? Safe means 60 years. Okay. Some buildings are over-designed, bridges are over-designed, they go far beyond 60 years. The Romans were certain about their stability of their structures, so we have now structures 2,000 years and they are still performant. But that's a different issue. So how much resources do we spend for this target of performance? So we need to know where we are heading. Then we need to know the mechanism of action. Continuing in this same example about structural safety, structural safety is a relatively recent concept, so maybe less than 200 years, that we understand material properties, the elastic plastic models, and in some aspects of structural safety, say spectrum response in earthquake, it's the 90s, it's less than 30 years, and it's not over yet, and we see it everywhere. When we're talking about, I don't know, foundation isolation of nuclear reactors, it's work in progress. Or probabilistic assessment of bridge stability, it's work in progress. So, and there are several uncertainties about loads evolution, about decay mechanisms, how the two, anyway. So the mechanism is to be known. You may ask me, yes, but we don't have mechanisms in toxicity of materials. Well, it's not entirely true. Some of them we know perfectly. Nitrates, what they do in the body, we know perfectly. Endocrine disruptors, we know perfectly what they are doing. So some mechanisms we know very, very well. What do we do about this? I'm not so sure that we exploit this mechanism knowledge towards our safe by design. And then comes, of course, the cost item. We are living in a cost-based world, so it's engineering in science, it's the pure knowledge. There's difficult distinction between the two. It's rather methodological, but let's not analyze that now. So the life cycle, not assessment, life cycle costing. So from beginning of the research towards the end of life of the materials is a critical item that needs to be taken in this by design. So the question is, again, tell me what you want to achieve. I want an opera house, 200 years, Sydney. Okay, tell me what you want to achieve, and I tell you what it costs, because I know everything in it now. I know all the mechanisms, and then you take a decision where the balance will come. That's by design. Concluding, you must say something about the venue here, huh? Remember, Venice was at the cutting edge of innovation and technology for centuries. But it dissolved little by little, and at the end has become just a nice destination. And hopefully someday will become again innovation center. But I have a little anecdote to tell you where Venice excelled, but not in the manner that you wish. What was the material that was the most expensive ever, and for 3,000 years, or from the Minoan times, now I'm taking more time, okay, let's finish this, just a couple of minutes. From Minoan times, and totally useless today. No, a hint. It's in the Minoan tablets. The name in ancient Greek is Stypteria. Modern Greek, Stypsis. English word, styptic. Come on, no hands raising. Styptic. Nowadays you find it in a barber shop. If you cut, they put a little crystal on this and the bleeding stops. But then you have the natural crust. Horses, when they are bleeding, they're using this. Stypteria, Stypsis, alunite, alen in alunitis. The story is that this was used in textile dye stabilizing. Textile dyeing was top business in Venice and later in Toscana. And the material was coming from the Greek islands, Lesbos. And when the Sultan took over, so the Ottomans took over, so he immediately increased the prices. So they had to pay, give all the profits they were making from textiles to the Sultan. So what the Pope did, he went to Lesbos, he found some technicians there, brought them to Toscana and started producing alunite in Toscana. But the Greek islands was better material. So if you would buy, or if you would smuggle, that's what the Venetians did, if you would smuggle in Italy alunite from Greek islands, the price was enormous, excommunication by the Pope, which meant that no man was allowed to make any more business with you. So, material science, that's the future. Good luck and best luck for your research. And thank you very much for your attention.